Welcome to another section of vector calculus. The plan today is we will talk about double integrals and volume. If you remember last year, you talked about integrals of f of x dx. And what they gave us is they gave us the area under a curve below f of x above the x-axis as long as f of x was positive. We're going to be looking at double integrals. We want to work with, instead of functions of one variable x, we'll look at functions of two variables, x and y. And instead of area, since we're bumping up a dimension, we're going to move into volume. So we'll start out with approximating volume. If you remember last year, when you started out by trying to find area, what you did is you placed a bunch of rectangles above that region, which weren't perfect in terms of covering the region, but we're close. Well, we're going to bump up a dimension. So instead of looking at rectangles, we're going to be looking at many, many rectangular solids to approximate the volume of the solid that we're going to be looking at. Then after that, we'll realize, just like we did last year, that the approximation doesn't quite work, but if you take a limit as the width went to 0, then you got the perfect area. Similarly, we're going to define the volume by taking a limit as, instead of the width going to 0, as a rectangular area going to 0. And that will be defining the double integral. Then we'll get into Fubini's theorem. Sounds magical, not so, but it's a cool name. And this is a guy that realized that we can look at x and then y, because that's the alphabetical order way of doing it, but we can also look at y then x. Either direction works, and it turns out no matter how you look at it, you get the same answer. And we'll talk about that. Then we'll see that there's some integrals that you can't really integrate if you keep one variable constant. But if you switch which variables first, you can integrate. And that is going to allow us to integrate functions that otherwise wouldn't be integrable in any means except maybe power series. So we'll have an example of that. And then we'll have some applications. We'll calculate volume, we'll look at average value, all kinds of fun stuff with double integrals. Let's start out with approximating volume. So here is an example. What we have here is a surface. This is kind of like maybe a paraboloid. And we have the xy plane. And in between the xy plane and the paraboloid is a region. Our goal is to find the volume of this region. So instead of cutting up into rectangles and finding the area of each of the rectangles, we're going to cut it up into rectangular solids. And the way you do that is you make a grid out of the xy plane. Then for every one of these grid rectangles, you lift up that rectangle until you get to the surface. And what you'll get is you'll get a little rectangular solid, not exactly, but close enough. And we'll be able to find the volume of that rectangular solid. So if you remember, the volume of a rectangular solid is the base times the height of the rectangular solid. So the area of the base times the height. But the base is a rectangle. And the area of a rectangle is the width times the height of that rectangle. Width is going to be dx. The height is dy, because these are the little rectangles in the xy plane as the base. Height is how high you have to go up. That's exactly what the function f of xy measures. It measures the height. So that tells us the volume of this little rectangular solid is going to be f of xy times dx dy. We can also write it as f of xy times dy dx. And we'll find they're both going to be helpful to understand how to do those. Also, notice that this is not quite a rectangular solid, but if we look at really small rectangles and we have a function that is continuous, then the function at any point in that little tiny rectangle is almost the same. That's basically the definition of continuity. So that this volume formula really does work with a very small error. And that's why we say we're approximating the volume instead of getting the actual volume. The volume of one of these rectangular solids is not the volume of this entire solid. To get the volume of the entire solid, we're going to have to add up the volumes of each of the little rectangles. So when you add up and you have a grid, you can say we're going to add this one, then this one, then this one. We will go along the x-axis, and then we'll move up to the next row and go along the x-axis again until you get them all. This is going to be a double sum because we're adding along the x and along the y-axis. So that gives us the big formula of the day, which says that the volume of a region below the surface f of xy and above the xy plane, if f of xy is positive, is going to be a double sum. We do a double sum because we're adding along x and y of f of xi yj. So that means we're looking at the ijth rectangle, and xi comma yj is some value in that rectangle. And we saw before if f is continuous, then that value will be almost the same anywhere in that little rectangle, times delta x times delta y. So let's look at an example of using this approximation formula. So the question states, approximate the volume of the solid that lies below the surface f of xy equals 2 minus 0.5x minus y squared, and above the rectangle in the xy plane with vertices 1, 0, 3, 0, 3, 1, and 1, 1. Use delta x equals delta y equals 0.5 and the upper right corner to approximate the function. By the way, here's the picture. Here's the surface, f of xy. Here's the xy plane. We're looking above the xy plane, below the surface, and we'll see a solid. We want the volume of that solid. So the way we calculate it is we look at the shadow of that solid, which is going to be this rectangle. That rectangle has vertices 1, 0, 3, 0, 3, 1, and 1, 1. So we get this rectangle. We want delta x and delta y to be 0.5. So I'm going to walk 0.5 units to get to 1.5, and then another 0.5 to get to 2, and another 0.5 to get to 2.5, and another 0.5 to get to 3. And I'm also going to walk upwards, up 0.5 to get to 0.5, and then up another 0.5 to get to 1. We want to use the upper right corner of each of these rectangles. So I'm going to draw the upper right corners of each of these 8 rectangles. Notice that the first rectangle's upper right corner has coordinates 1.5, comma 0.5. This next one has coordinates 2, comma 0.5, etc., etc. What I want to do now is evaluate the function at each of these points that I'm looking at. So f of 1.5, comma 0.5 is 3 minus 0.5 times 1.5 minus 0.5 squared, and I calculated that, and it's 2. I did f of 2 comma 0.5, same idea, I plugged in and I got 1.75. Then I did f of 2.5 comma 0.5 and got 1.5. And I kept going for each of these 8 points that are the upper right corners for each of the 8 rectangles. And the last one, for example, is this point right here, which is 3, comma 1. And f of 3, comma 1 is 0.5. So there is our set of numbers that the function gives for the 8 points we're plugging in. Now we have delta x equals delta y equals 0.5. So we can say that delta x times delta y is 0.25. 0.5 times 0.5 is 0.25. Now we're ready to plug in to this formula. This double summation means add them all up. So I do that. And we can say the volume is approximately equal to, and I'm going to factor out the delta x, delta y at the end. So I'm going to have a big sum times 0.25, and I add the numbers. 2 plus 1.75 plus 1.5 plus 1.25 plus 1.25 plus 1 plus 0.75 plus 0.5. Those were each of the function values. If you plug that in your calculator or do the arithmetic, you end up with 2.5. And that is the approximate volume of the solid bounded above by the function f of xy equals 3 minus 0.5x minus y squared, and bounded below by this rectangle here. We want better than the approximate volume. Approximating is good. It's also a lot of work. If we have a function like this, wouldn't it be nice to get the exact volume? And the good news is we can take our cue from last year. Last year we did the similar thing when we looked at area under a curve. So now what we're going to do is, instead of letting delta x and delta y be 0.5, we're going to take a limit as those delta x's and delta y's go to 0, or in other words, we're going to let the area of each of the rectangles get smaller and smaller and smaller and smaller until it approaches 0. And that gives us our big definition of the double integral. Here's what it says. Let z equal f of xy, and let R be a region in the xy plane. Then the double integral of f over R is defined by, and we get a double integral sign. There's 2 integrations here. Over R, our region, of f of xy, dy dx, and that is equal to the limit as delta A approaches 0. What that means is we're going to take the limit as the areas of each of those little rectangles we're going to use approaches 0, that we're going to squish those rectangles in. The double sum of f of xi yj times delta aij. That delta aij is going to be the area of the ijth rectangle. And then, if the function happens to be greater than or equal to 0, then we can say the above integral defines the volume of the solid below z equals f of xy and above the region R in the xy plane. So we can get the exact volume now using this double integral. So now let's look at some properties of double integrals. We saw in first year calculus that there were lots of good properties that you can use to find integrals. Just about all of those properties are going to still hold analogously for double integration. So here's the first one. It says that the double integral over a region of a constant times f of xy dA. So if we multiply the function by a constant, we can pull the constant out. It's equal to the constant times the double integral over R of f of xy dA. And that's the same idea as we did with single integration. You can pull the constants outside. The second one also comes from single integration, and that says that the double integral over R of f plus g dA. So if you add two functions inside the integral, you can split that up as two integrals. Say that's equal to the double integral over R of f dA plus a double integral over R of g dA. Again, we've seen this in single integration. Another one, which we've seen before, is that if f of xy is greater than or equal to 0, then the double integral over a region of f of xy dA is greater than or equal to 0 also. We've seen that in single integration. We can also think about this as it has to work, because if f of xy is greater than or equal to 0, then the double integral over R of f of xy dA represents the volume. And volumes can't be negative, so of course it's going to be greater than or equal to 0. So these properties should be pretty clear. Let's look at the next one. It says that if f of xy is greater than or equal to g of xy, then the double integral over the region of f dA is greater than or equal to the double integral of g dA. Again, that should make total sense, is that since we're adding up f times dA versus g times dA, if f is bigger than g, then f dA is bigger than g dA, at least in the approximation. So the double integral of f dA will be at least as big as the double integral of g dA. The next property, and the last for today, states that if we have a region R, and we're going to look at the double integral over R of f dA. And R could be split up into two pieces. One piece is R1, the other piece is R2, and they don't overlap. So R is a union of R1 and R2, and the intersection of R1 and R2 is just the empty set. Then the double integral over R of f dA is equal to the double integral over R1 of f dA plus a double integral over R2 of f dA. Those are properties that will be useful. Most of the time you're going to use them without thinking about it. You're going to be double integrating a sum by integrating one at a time. You're going to be pulling out constants. You're just going to be doing it because it's the right thing to do. Nothing too magical about these properties. Let's look at an example. Let's suppose that we want to find the double integral over the region R, x e to the y over 2 dx, where R is the triangle with vertices 1, 1, 3, 1, and 1, 2. So let's start by sketching a little bit. Again, this is something that you probably will not want to do by hand. I didn't, that's for sure. It turns out you don't have to sketch it, but it helps. So what we have here is we have x e to the y. I used a computer. We get this beautiful little surface, kind of cool. And our triangle in the xy plane with vertices 1, 1, 3, 1, and 1, 2. And if you go above that triangle and below the surface, then that's going to be the volume, and that is what this double integral gives us. We don't need all of this to answer the question. All we really do is look at the triangle. So here's the triangle. We have the vertex 1, 1, so I plotted 1, 1. We have the vertex 3, 1, I plotted 3, 1. And we have the vertex 1, 2. I plotted 1, 2, and made this beautiful triangle. Now comes the fun little part. I draw integral man. This is integral man. Notice he's happy, and of course he's happy because he's integral man. Everyone's happy when they do math. At least I am, and I think you are too. What this integral man helps us understand is we're going to look at the integral man's feet, and we're going to look at the integral man's head. So the feet are down here, and the equation of this curve, in particular it's a horizontal line, is y equals 1. Now for the head is sitting on this curve, which is a line, not horizontal. In fact, the slope of the line we go down 1 over 2, so the slope is negative 1/2. And then if we plug in 1, we're supposed to get 2. So if we plug in 1, negative 1/2 times 1 plus 5/2 really does give us 2. You can check that. However you do it, you need to know how to find the equation of a line if you're given 2 points. So we know that the inside integral is going to go from 1 to negative 1/2 x plus 5/2. To get the outside integral, now the little man gets to do some walking. And you want to see how far to the left can that little man walk. That little man can walk all the way to the left at x equals 1. And how far to the right can that little man walk? That little man can walk all the way to 3. Of course, he's going to shrink as he goes, but that's okay. He's a little happy man, so he can do that. There's our integral. The way we write it is our outer limits are going to be x equals 1 to x equals 3, because that's the left and the right the little man can walk. Inner limits are going to be y equals 1 to y equals negative 1/2 x plus 5/2. Then we have x e to the y, that's the integrand. Notice that it is dy dx, because the inner limits talk about the y coordinate, y equals 1 and y equals negative 1/2 x plus 5/2. So that's why dy first. The outer limit is dx because x equals 1 to x equals 3 is what the 1 and the 3 represent. To evaluate a double integral, we turn it into an iterated integral. We can write this double integral as the single integral from 1 to 3 of the single integral from 1 to negative 1/2 x plus 5/2 of x e to the y over 2 dy dx. Now let's do this single integral. When we're talking about a dy, that means x is treated as a constant. Since x is a constant, we just need to integrate e to the y over 2 dy. We can let u equal y over 2, du equals 1/2 dy, or 2 du equals dy. And then the integral of an exponential is itself. So we end up with still the integral from 1 to 3. And now we've integrated x e to the y over 2 and got 2x e to the y over 2. And that's from 1 to negative 1/2 x plus 5/2 dx. Now let's plug in. And when I plug in, if you plug in the negative 1/2 x plus 5/2 into y, you get negative 1/4 x plus 5/4 because we're dividing by 2. And if you plug in 1 into y, we just get a half. So we end up with the integral from 1 to 3 of 2x times e to the negative 1/4 x plus 5/4 minus e to the 1/2 dx. I'll let you figure out how to integrate this. If you're allowed, you can use a calculator or a computer and get an answer. If you're not, then the technique for this is integration by parts. However you do it, you should get something around 3.213. And what we found, because this is a positive function, we found the area under the surface. F of xy equals x e to the y over 2 above this triangle is 3.213. It's now time to talk about Fubini's theorem. And here's what Fubini's theorem says. It says if we have a double integral over a region of f of xy dA, we have a couple choices. One choice is what we did last. We first took our little man and said, where are little man's feet? Where's the little man's head? Look at those two curves and let him walk left to right. And when we do that, we get an integral where the inner limits go from y equals g1 of x to y equals g2 of x, and x going from a to b. And then we have a dy dx. We could do it the other way around. Instead, we could have our little man lying on its side. And instead of thinking about how high the head goes and how low the feet are, we can think about how far right the head is and how far left the feet are. And look at those curves as functions of y that give you an x. So we can say that this double integral of f of x y dA is also equal to the integral from c to d. Now, instead of x going from a to b, y goes from c to d. And the inner limits will be x equals h1 of y and x equals h2 of y. So that's the feet and the head of f of xy dx dy. So notice this is not some little commutative property multiplication. You can't just switch dy dx and get x dx dy. If you do switch the dy dx to get dx dy, we must also redo the limits of integration. And that's Fubini's theorem. It says no matter how you do it, whether you first look at y, then look at x, or first look at x, then look at y, you always get the same answer. So here's an example where we're going to have to use Fubini's theorem. Let's suppose we have a double integral from 0 to 2 and from 2x to 4 of e to the y squared dy dx. You could try integrating this, but you may remember from first year calculus, if you try to integrate e to the y squared dy, you get into all kinds of problems. U substitution doesn't work. Nothing is going to work. The only way you could possibly do this is with power series. And I don't want to go there today. Maybe you love power series, but it's not what I'm going to do because that is a mess. We'd rather do it in what's called closed form. So to do that, we're going to look at the picture. So here's the picture. We can say that y goes from 2x to 4. Y equals 2x is this line through the origin. Y equals 4 is this horizontal line. And x goes from 0 to 2. X equals 0 is the y-axis. And then the little man can walk as far as x equals 2. And notice if you plug in 2 to 2x, you get 4. This is a triangle. Well, this doesn't work because we weren't able to integrate. So the trick is we're going to use Fubini's theorem. And we're going to take that little man who's standing up, getting all tired, walking up this hill. We're going to give him a rest, and we're going to let him walk horizontally. So there's our little man smiling even more. And now we can say, where are the feet? Well, the feet are at the equation x equals 0. And the head is at the equation x equals y over 2. The little man can walk as low as y equals 0 and as high as y equals 4. So we could switch the order of integration and write it as the integral from y equals 0 to y equals 4. The little man goes down to 0 and up to 4. And the integral from x equals 0 to x equals y over 2 of e to the y squared, and now it's dx dy. Seems like not much of a big deal, but that changes everything. Because integrating e to the y squared dx is a piece of cake. Because e to the y squared is a constant. The integral of a constant is just x times a constant. So we can write this as the integral from 0 to 4, x times e to the y squared, from 0 to y over 2 dy. Now I can plug in. If I plug in y over 2 for x, I get y over 2. I can pull out that over 2 as a 1/2. That was one of the properties of integration. We can write this as 1/2 times the integral from 0 to 4 of y e to the y squared dy. Notice if I plugged in 0 for x, I get 0, so I didn't write that part. And now it's basic integration. We know how to do this. unlike before when we tried to integrate e to the y squared dy and u substitution didn't work, now we have y e to the y squared dy. And u substitution is beautiful because the derivative of y squared is 2y. So we can say that if u is y squared, then du is 2y dy. We can say that dy is just du over 2. And that gives us the over 2 becomes 1/2 times 1/2, which is 1/4, e to the y squared, because the integral of e to the u was e to the u, from 0 to 4. And now I plug in. E to the 4 squared is e to the 16th. E to the 0 squared is 1. So I get 1/4 times e to the 16th minus 1. And that's the answer. And we didn't have to go into power series and all kinds of fancy stuff. We just had to let the little man be horizontal instead of vertical. Now let's talk about average value. It's one thing that sometimes is used in physics and other places, in economics. So let me give you the definition. It's very similar to the definition of average value for one variable functions. If you remember, the definition for average value for one variable functions was 1 over b minus a times the integral of f of x dx. So instead of b minus a, which is the width of our interval, we're going to be looking at the area of the region. We say that the average value of an integrable function over a region R is defined by 1 over the area of the region, A, times the double integral over that region R of f of xy dA. Here's an example of finding the average value. What we have is a metal plate in the shape of the disk, x squared plus y squared is less than or equal to 4, has temperature T of xy is equal to 6x squared y squared. Find the average temperature on this metal plate. So as usual, we start by sketching in the xy plane what the region looks like. In this case, x squared plus y squared is less than or equal to 4 is a disk, so it's a circle of radius 2, centered at the origin. And if I solve for y, I get y equals plus or minus the square root of 4 minus x squared. So when I put the little man in this disk, I notice that the little man's feet are at y equal negative the square root of 4 minus x squared, and the little man's head is at y equals positive the square root of 4 minus x squared. If the little man walks over to the left, the little man can get over to negative 2, and the man can get out to the right to positive 2. So now I could put this together along with the definition of the average value, the double integral. So notice that the area of this circle is pi r squared, and r is 2, so that area is pi times 2 squared, or 4 pi. So I write 1 over the area, or 1 over 4 pi, times the integral from negative 2 to 2. Again, the farthest left was negative 2, the farthest right was 2, of the integral from negative the square root of 4 minus x squared to positive the square root of 4 minus x squared. And then the integrand is 6x squared y squared. We have dy dx because the little man is standing up and down. So now I need to integrate that. 6x squared is a constant with respect to y. The integral of y squared is y cubed over 3, and 6 over 3 is 2. I get 1 over 4 pi. We still have the integral from negative 2 to 2. There's a 2. And then we have x squared y cubed, because y squared became y cubed over 3. And then from negative the square root of 4 minus x squared to positive the square root of 4 minus x squared dx. Plug those in. Notice that if we have y cubed and we're plugging in negative root 4 minus x squared and positive root 4 minus x squared. I subtract those. Well, if you have a positive minus a negative, that gives you twice that amount. So that 2 is going to become a 4. I still have 1 over 4 pi. I have an integral from negative 2 to 2. And we have a 4x squared. And we had plugged in a 4 minus x squared. We have the cube of the square root is the 3/2 power times dx. I worked that out in my calculator. This is just a single integral. We could do it by hand, but that's a lot of work. And I got 4. We can say that the average temperature on this metal plate in the shape of the disk is 4 degrees. Really cold, whether it's Celsius or Fahrenheit, I didn't mention, but it's 4 degrees. So now let's find the volume between two surfaces. So the good news is we've already explored something similar last year when we looked at first-year calculus. In first-year calculus, you figured out how to find the area bounded between two curves. And you looked at the top minus the bottom. So if we want to find out the volume between two surfaces, we do the same thing. We're going to look at the top minus the bottom. So here's an example. The question states, find the volume of the region bounded by z equals x squared plus y squared and z equals 3 minus 2y. So it's a good idea to take a look at it. I used a computer. Z equals x squared plus y squared is a paraboloid. Z equals 3 minus 2y is a plane. We're looking at the volume of that part of the paraboloid below this plane, and that is a double integral. You don't really have to completely get the three-dimensional surfaces drawn in beautiful color like I have. All you really need to know is which is top and which is bottom. And here the top is a plane, the bottom is a paraboloid. What we do need is the intersection. To find the intersection, we're going to set them equal to each other because we have z equals x squared plus y squared and z equals 3 minus 2y. We can set x squared plus y squared equals 3 minus 2y. And then I can do some algebra magic. I can add 2 to y to both sides, and I can complete the square. And I get x squared plus parentheses y plus 1 quantity squared is equal to 4. So the good news is we know what this looks like, and we can have a little happy man. And we can say that we have a circle of radius 2 centered at the point 0, negative 1. Put the little man in that circle. We could solve for y. We could say that y is equal to negative 1 plus or minus the square root of 4 minus x squared. So the little man's feet are at negative 1 minus the square root of 4 minus x squared. And the little man's head is at negative 1 plus the square root of 4 minus x squared. And then the little man could go as far left as negative 2 and as far right as positive 2. So we could put all of this together to find the double integral. We're going to integrate from negative 2 to 2. That's as far left and far right. And then an integral from negative 1 minus the square root of 4 minus x squared, that's where the feet are, to negative 1 plus the square root of 4 minus x squared, that's where the head is. And we're going to take the top minus the bottom. The top is a plane, 3 minus 2y, and the bottom is the paraboloid, x squared plus y squared. We have dy dx because the little man is standing up, top to bottom, so that's a dy, and then dx. I used a calculator to integrate this, or a computer actually is what I used. And I got about 25.13. Depending on what your instructor asks you to do, you should know how to do it by hand. You should also know how to do it by technology. We can conclude that the volume bounded by the paraboloid z equals x squared plus y squared and the plane z equals 3 minus 2y is about equal to 25.13. That's all I have for today. So hopefully you understand how to calculate double integrals. Know that the double integral represents the volume if the function is positive. understand the average value of a function and be able to find out what the volume is between two surfaces. And that sometimes you want to go dy dx, sometimes you want to go dx dy, and Fubini's theorem tells us we can do either of those. So until next time, have a wonderful day, morning, evening, wherever you are, and have a great week. Thank you for watching this video.